Thank you very much. Thank you. Thank you. Thank you. Thank you. Woo. I'm still alive. Oh, that's Cripple Creek. Alrighty. New Cripple Creek. Let's celebrate. Okay, so I'm going to do a couple examples, and I'm going to have you guys do some of your own so we can see if you can do it. Okay, so the first example is this, and then if it's not asking too much, if you can pan the camera now so I can see the screen. Oh, I don't want to erase that, right? Okay. Oh, there we go. That's beautiful. That is beautiful. Thank you. Okay. So here's this thing, and it's at the top of the hill, and it's moving right along. Okay. And then it's going to roll down the hill, and the question is, what's the velocity at the bottom, right? And so before is going to be, by the way, the top of the hill, and after is the bottom of the hill, right? There we go. And we want to put an equal sign in between those two situations, right? Now at the top of the hill, what has it got? 4.5. It's moving, so it's got what kind of energy? It's got kinetic energy, right? It's got some 1/2 mv squared, right? And then these guys are easy. It's either moving or it's not, right? It's either on a hill or it's not. You can, see it from the diagram or read it out of the question, right? Okay. What else does it have? When it's moving at the top of the hill before. It's got potential energy, doesn't it? How do we know that? It's on the top of the hill. It's not at height equals 0, right? Height equals 0 is this little dotted line there, arbitrarily determined, right? And so it's not at height equals 0, so it's moving, and it's got potential energy, right? So it's got mgh. At the bottom of the hill, where does the energy go? It's all kinetic, isn't it? Right? It's spent its potential energy and turned it all into 1/2 mv squared. And these v's are different v's. Okay? Right? And now we can just plug in numbers. Kinetic and potential turns into just potential, and that's why you're going faster at the bottom of the hill, right? So we go 1/2 250 times 4.5 squared plus 250 times 9.81 times, what is it, 1.75, right? Equals 1/2 times 250 times v squared, and we don't know v, yeah? Now, before you go and stuff it into your calculators and get the answer, which I will ask you to do, what if we had a different mass? Would the velocity at the bottom of the hill matter? Wouldn't matter, would it? Because just mathematically, don't try to think too hard, right? Mathematically, can't we divide 250 out of all of those, and it won't have any effect on v? It just cancels out. So if it's just mgh's and 1/2 mv squared, then I call these roller coaster problems, right? That's what a roller coaster is, right? The m doesn't matter. This is why when you did a lab and you put extra masses on your cart and it rolled down the plane, did that have a huge effect on the time it took to go down the plane? A little bit, but not a huge effect. It only has an effect when there's a lot of friction. Sometimes extra mass helps you overcome friction, right? So take your calculator now and see if you can calculate what v has got to be on that side. And if you are talented and gifted, and I know 2/3 of you are either talented or gifted or possibly both, right? See if you can do it in just like one swell foop, like you just hit enter once and you get the answer. That is 4.5. So you can do it with the v, or you can leave the v out if you want. You don't need to show me the answer. We'll just all. Do you guys get 7.388 or something like that? And sadly, we only have 2 sig figs, so we'd have to say about 7.4. Yeah. And some people, this is a different kind of problem, isn't it? Some people like these problems. Some people don't. But the key here is to really focus on trying to learn these to see which one you are, right? Maybe someone that just it comes naturally to, right? Eventually you'll do it. Eventually it'll click for you and you'll understand it. Make sure it clicks for you before the test. That's just a kind of a suggestion. Okay, are we ready for another Nutter Butter? We're calculating. Da 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 da. Class. So here's our second example. And I'm going to ask you to add something to your notes that'll be crucial here. Okay? These guys are easy. When you're looking at a problem in terms of before, can I interrupt, guys? When you look at a problem in terms of before and after, these guys are easy. You're either on a hill or you're not. If you can draw the picture, this is really simple. You're either moving or you're not. The spring is either compressed or it's not. Okay? But force times distance always gives kids a problem. And that's because the force times the distance can happen throughout the entire problem, can't it? It's like the force in this case is exerted on the thing the whole time. It's not before, it's not after, it's like during. Yeah? You know what I'm saying? Right? So when you set that thing up with force times distance, my clue to you is put stuff on the left side. Think in terms of acids. So if the force speeds you up force times distance, right? Put it on the left side. It's an acid. It's something giving energy to the system. If it's something like friction, typically, right, that slows you down, put it on the right side. It's an expenditure, right? It's where the energy went. Slows you down, force times distance, then it's going to go on the right side. So for this problem, which is it? Obviously there's a force times a distance. This is a slows you down force. It hits a puddle and it slows the car down. This is the Fred Meyer parking lot, right? Like they repaved the lot and they left this low spot there that gets this spectacular lake. By the way, don't drive through that lake. Modern cars have these $800 things called catalytic converters. They glow red hot sometimes. Do you suppose it's a good idea, and they're, by the way, on the lowest point of your car, just about. Is it a good idea to immerse that in water occasionally? Not so much. Not so much to like quench it, you know, by sticking it in the water, right? But before I had to replace my catalytic converter, I used to hit that puddle as fast as I could, and just you can make like a tidal wave on the next car, right? It's kind of a fun thing, right? Okay, so in this problem, clearly there's a slow you down force times distance. What else do we need? What else do we need? Is there any, guys, is there any hill in this problem? No, there's going to be no MGH anywhere. Is there any springs? No springs. Okay. What do you suppose there is? Kinetic energy, right? Is it moving to begin with? Is it moving to end with? Well, presumably, because it asks you for what's the velocity, right? So presumably we've got kinetic energy before, 1/2 mv squared. Afterwards, we've got, where did that energy go? Well, some of it went to work against the puddle. Some of it is still left in the form of kinetic energy. Yeah? Does mass cancel out of this one? I don't think so. I don't think it's gonna, because there's no m in here. Which means, by the way, that the more massive the car, the easier it's for it to go through the puddle, which makes sense. It's got more inertia, right? And now we can just plug in 1/2 890 v squared is equal to, what is it, 3,200 newtons and 3.6 meters, right? Plus 1/2